We are
Okay,
recording. Cool.
recording. All right. Programming in Idris, writing formally correct programs. All right, forget everything you know. Um, so the first thing is you can make data types. And this should be reasonably intuitive. I'm making up a thing called flavor, and it has chocolate, vanilla, and strawberry. And then, so then I can say, then the other thing you can do besides making data is you can make functions. And so I'm going to say, I'm going to make a function that if you give me a flavor, I'll give you back. Actually, we don't know what Booleans are, so we'll. Okay, you give me a flavor and I'll decide whether it's yummy or not, all right? Gary has a crinkled brow. All right, so I'm going to pay attention to that. Okay, and then I can ask Idris what it thinks of this file. In Emacs, that's Control C, Control L for load. Okay, and it says everything's cool so far, but you haven't really finished your definition of what yummy is. Okay. I've just said I've told the type of yummy, but I haven't told it how to effectively compute the function. So I'm going to ask Idris to start filling things in. In Emacs, you go Control X, Control S. I guess it's not in the menu here. If you use Atom, there's keyboard shortcuts in Atom too. Why did it not do what I wanted? Control X, Control S. Oops, Control S. Wait a minute. Control C, Control S. Yeah. Okay. So it can automatically sort of start the definition for you, and you can ask it what it thinks so far. And so far, we know that X is a flavor, and we have to come up with a decision about yes or no. All right. We can also ask the computer a little bit more about X at this point. I can do a Control C, which means case split. So it'll break down X. There was only 3 possibilities for flavors, right? There's chocolate, vanilla, and strawberry, right? And then over here, the kinds of things you can do is you can ask it to automatically figure it out, Control C, Control A, but it doesn't really know. Oh, that was interesting.
Oh, you just know what is yummy, right?
I wonder if it's just going to pick the first constructor in every case.
I think it does.
All right, but suppose that I don't like strawberry, so I'm going to actually tell it. So that surprised me that I thought it would only pick things that were necessarily the case. Maybe it just picks any thing that it can find that satisfies the type. All right. So
Yeah.
And Dan, are you able to increase your font size 1 or 2 levels by chance?
I thought it was already pretty big, but let's see.
I'm just thinking for when people watch this later on as well.
Well, if it's sufficient for the participants, I'm going to leave it this way because people watching later can do things with their screen.
Okay.
Is it big enough for you to see comfortably?
Yeah.
Okay.
Yeah, I'm good.
All right. And then if I forgot to do one, Idris is okay here, but if I say total, what?
Is there some character in front of total? Or no?
Hold on. Try it again here. Starting, checking. Am I not checking? Oh, it's already checked the file and saved a thingy. Okay, so there's no such thing as no X, but so if I check it again, right. Function yummy is not total as there are missing cases. And I can even say Control C, Control M, tell me what the other cases are. There's the one I forgot. I don't know why I didn't make a new line there. And yes. And so we're going to go up here and put so we're trying to write programs that are necessarily correct. And if you write incomplete definitions, then at runtime, your program can get to there. And, and then if you have this program and you run it and you ask it whether vanilla is yummy or not, it'll crash. So we always have to have complete definitions in order for our program to be correct. Steve, does this sound okay so far?
Yeah.
All right. Now, traditionally, yes, no is called Boolean. Is it bool or Boolean? Right. Okay. And actually, there's something in the standard library called yes. Let's see. Those are not necessarily the same thing. Okay, so we'll decide that that's true. Okay. Now the next thing you can do is you can say data oh, I should explain what I'm. Okay, so garnish doesn't use any new mechanics, right? It's just like flavor. We can make things up. One of the colors are red are data and blue are types. And I guess green are functions. Okay, so garnish is just, making lists of thingamabobs. All right, now this optional thing, we got nope or some, but then we've got this A here, okay? And that's saying that to make an optional thingy, you not only choose between nope and some, but you choose some type. The A starts as a lowercase letter, so it's like a type variable. So any type can go here. And so this constructor is either, it constructs nope or some with an A inside of it, all right? So if we want to order some ice cream or order a dessert, this one just has one constructor. We don't have any other stuff over here. And it's called make order. But it's got, just like some has an A here, you can have thingies after, you can have arguments to your constructor functions is what these are called. These are actually constructor functions. Chocolate is it constructs a flavor, vanilla constructs a flavor, strawberry constructs a flavor. And they don't take any arguments. They're kind of zero-ary functions. But some takes one argument, and make order takes two arguments. And its first argument is a flavor. You have to give it a flavor, and you can optionally give it a garnish. All right? Let's see what the computer thinks of that. It thinks we're okay. And then I can say, Gary, see what it thinks of that. All right, it says, okay, well, okay, Gary's going to order something, but we don't know what yet. So, Gary, what are you going to order? And then we're going to Control C, Control S. What are you going to order, Gary?
Chocolate with whipped cream.
Like that?
Yeah.
Okay, let's see what the computer thinks of that. So it's got too many arguments for chocolate. So it thinks that we're trying to pass whipped cream as an argument to chocolate. What do you think we forgot here?
An and. No.
Let's go back and let's forget everything we know again. What is an order? How do you make an order?
It's a flavor and an optional garnish.
Right, but what else is it? Like to make a flavor, what did we have to do?
Flavor, we had to.
We had to actually say chocolate, right?
Yeah.
So to make an order, we actually have to say make order, right?
We need to use
Yeah.
Let's try that. Okay. So now what's wrong?
It doesn't like the expected type mismatch between garnish and optional garnish.
Right.
Garnish and optional garnish.
How do we make an optional garnish? There's only two ways to do it.
Oh. Nope and some. Some.
There you go.
Some.
And then I'm going to add some parentheses and I'll explain why maybe. Ooh, look at that. Somebody else make an order.
Make order.
Okay, so Steve, order. Okay, so we've got equals make order strawberry. And then nope. Now, if you use nope, then that's the end. We're not indicating that we don't want to garnish.
Right. Okay. And then I'm just going to explain the one thing, which is why we had the parentheses here, or parentheses is one way to do it. So it's saying it doesn't understand that it thinks there's a type mismatch between optional A and garnish.
Optional A, make order.
So the way this works, go ahead.
Oh, I would just want to say that sum is here as an argument, but sum is type constructor and not just the type.
Right. The way this gets printed, the way it thinks about this is like this. Functions, there's really only functions of one argument. And a function of one argument basically takes its argument and gives you back a function of one argument and so on. So we have to tell it that, oh no, don't parenthesize it that way, parenthesize it this way. And then in order to help read some code that you'll see later, you can also do this. And basically, $ is defined as A to B, and it's just low precedence. So it's basically sort of like this. I don't know how to explain the $ very well.
It's really just this parenthesis that you showed, as you showed first.
Yeah, it works the same way as this. And I should be able to say, well, there's no magic and explain how it works, but I'm just going to it's nicer sometimes to have less parentheses. And I think you can sort of always add $, and it never really screws things up. Well, that one, it'll screw it up because the whole point was we want these two to stick together closer than the ones over there.
One way to think about $ is think about this as this stop in a sentence. So you need to stop and think what's next phrase. Next phrase is a whole statement. I heard something like that.
Maybe you can also write in prefix format this $.
Oh, right.
So it will be visible the first and the second argument.
Yeah.
So it just means take the first argument. Oh,
It must be like part of the parser or something. I don't know. I'm confused at this point.
okay. Yeah.
Okay. Right. So there's a mild amount of mystery around the $sign, but otherwise, we sort of understand what's going on, right?
Yes.
That's it. That's all there is to programming.
Sweet. I get my diploma now to be as a developer.
Right. So I'm probably going to speed up, and I might not explain everything, but I'm pretty sure that everything that I'm going to do for the rest of the time is reducible to those sorts of things. We can make up data, we can make up parameterized data, and we can make up functions. Oh, actually, one other thing that needs explaining is that there's two ways to write these data type things.
Can you also show one simple example of dependent functions? When you, for example, accept optional type to decide result type.
Yeah, although in my mind, it's easier to just not think of them as special. Anyway.
Okay.
You can also write these as
and both of these ways to write data types are very similar to how you can do it with Haskell also.
similar to Haskell. Oh yeah, all this stuff is
Yeah.
very, very similar to Haskell. But again, we're forgetting everything we knew, right?
Yeah.
So let's see what the computer thinks of this.
You need a type of A in optional.
No, you actually don't.
No, but no,
Wow, this is hard. Hold on. No such.
and in the sum also.
Okay. So the other form is a little bit short for this. So this is saying optional is a thing that takes any old type and gives you another type. And there's two ways to construct it. One is that nope will give you an optional A. And the other one is that sum takes an A and gives you an optional A.
For me, this is like more clear representation. It exactly tells you, I have something that I'm creating a type, optional, and I have two constructors to create this type. And you see it, you see these two functions. So, yeah.
Is that cool, Gary?
Yes.
Okay.
If I may ask, why we say that we create a type in a data optional A, so create from A type. So optional odd A, I would think as thingy that is not a type, but is type applied. Well, never mind.
Well, yeah, optional is a type constructor, if you like. It takes some type and gives you a type called optional A.
Oh, now I get it. Yeah.
All right.
That's nice explanation. Thanks.
Yeah, it's similar. You can say in Haskell to start, or now you can also say type if you include the extension type types.
Right. Okay. So one of the, I think in Idris, the developer is this Edwin Brady, and he talks about type-driven development. And so you notice that once I've written the type, I could just ask the computer, like, what's the next stuff I should write? What's the next stuff I should write? And so Idris has an extremely expressive type system which gives the computer a lot of information about what's the next thing that could be okay here. All right. Where was I here? Okay. How much of this to explain? All right. So I'm reading a paper about a programming. Well, it's about a way of specifying programs or whatever. And so part of the paper says, okay, we're going to have this programming language that's pretty boring and normal, but the details of the programming language are sort of necessary in order to make the proofs work. And this is on the edge of my understanding of things, and so I have to read these papers very slowly and convince myself that I actually understand. And the way I convince myself that I understand is that I take the prose of the document or the Greek letters and stuff like that, and I write it in a programming language. And then I ask the computer, what do you think of what I wrote down? And if the computer smiles at me, then I think, oh, maybe if I could teach this stuff to a stupid computer, maybe I understand it. Right?
Oh, sounds good.
Okay.
So Dan, just so that's one use case for using Idris is you have a paper and you want to work through the mechanics of it.
Yeah.
Could another instance be where you want to, for instance, Rolang, you want to create a smart contract, but smart contract is maybe a little bit involved or complicated. And could one decide to do it first in Idris to make sure that their logic is correct, and then once that works, then go into create a Rolang smart contract? Would that be another reason for using Idris?
That's a possibility. I think the sort of roadmap for Rolang is that it eventually takes on most of the properties of Idris.
Okay.
So the interesting thing about our fun module here is that there's no bugs. I would bet you $1,000 that there's no bugs in this thing. All right.
Only 1,000.
What's that?
Only 1,000.
If you were willing to bet more, I would probably take the bet. But if you write total here at the top, and then and Idris thinks it's okay, then every function definitely obeys its type, and as long as the types say what you meant to say, then you got no bugs. And this is so different from the way programming is taught. Programming is taught with like C or Java or anything like that, and in almost every program you write has bugs. It's real, or at least, yeah. So, all right. So we get this programming, this paper about a programming language. And I used to have this file in the same order as the paper, but in Idris, in the paper, it'll do successive elaboration. It'll say this is an X, and by the way, an X is made out of an A, B, and a C, and an A is made out of a Q, R, and an S. In Idris, you can't do that. You have to define Q, R, and S before you can define A and A, and then you have to define things before you use them, unless you write a mutual block, and I didn't want to do that. Anyway. Okay, so there's some things that I don't want to talk about. Okay. Objects consists of a class identifier and a partial mapping from field identifier to values. All right, so that's not too scary.
These represents like instances of a class, right?
Right. So where did I define class ID? Oh. Okay. I don't know why I did it that way. Basically,
so you don't have a list of fields on the class.
Well, I'm just talking about the class ID so far. And I'm just going to use a slightly different name. Come on. Takes longer because there's more stuff. Thinking. All right. So using only the stuff that I taught you about ordering ice cream, basically I've said that class ID can be constructed only one way, and when you construct it, you give it a string. So basically class IDs are things like ABC, okay?
Mm-hmm.
Okay. And I've used this way of doing it for reasons that I only just barely remember, but it comes to the same thing. And then I also had to teach Idris how to tell when two class IDs are equal and when they're not. You would think that's kind of obvious. If they're the same string, they're the same class ID, but you kind of have to spell that out. And in fact, it's tedious, and I use the library to do it, but never mind. Okay, basically class IDs are strings where we know that they're class IDs, right? It's ABC used as a class ID, and not ABC used as a field ID. And then back to, okay. And so one of the ways of, so this parentheses notation is shorthand. Let's go back to our fun.idris. You can basically say data pair AB equals make pair AB. So this is using no magic here. Oh. So make pair is a constructor. There's two different arguments, two different types. And that's how you make pairs. And this parentheses notation is just shorthand for that, okay? So this parentheses says that there's a pair, and one of the type A is class ID, and type B is this thingamabob, all right? Now what's that thingamabob? So in the paper, it was written kind of field ID arrow value, or F arrow FV or something like that. So I spent a lot of time figuring out what I'm going to do to make that up. Okay. And let's go back to our fun thing. One of the things you can do is you can use symbols. So you can say infix 8 super rocket thingy. Okay. And then and that's a mixer, let's say. All right. And so, oops, yeah. Oh, it's going to be infix. So it's going to take two flavors and give me back a flavor. That is, it's going to take a flavor, give me back a function that takes a flavor and gives me back a flavor. And so Control-C, Control-S, how do we do that? No, I guess sometimes you have to put parentheses around these things. Okay, and it says, well, you haven't defined what rocket magic is, so nothing identifiable under point. I guess it's not as good. Sometimes these magic things don't work as well with the tool, I guess. But oh, right. Man, maybe I'm not allowed to use. No, I've used colons before and stars. Okay. Okay.
Don't you have an extra space somewhere at the end in infix? No, never mind.
Right. Okay. So we made up a special symbol here, and so it wants us to define it for chocolate, vanilla, and strawberry, and chocolate versus chocolate. Let's say that gives you strawberry, and chocolate mixed with vanilla gives you Oh, chocolate, say vanilla. Let's just do, and this means vanilla mixed with anything gives you back, let's say, chocolate. And strawberry mixed with anything gives you vanilla, let's say. What did I do? Oh, I've misspelled chocolate everywhere. All right, now it's happy. One of the things I forgot to mention is that now I can ask it, the read eval print loop you can actually compute. Okay, so we can make up our own symbols, and they're just normal functions. All right, they're in that green color. All right.
And we can use this on data types also, right?
I think so. One moment. Okay. All right. So I've got this. In fact, yeah, this is a type constructor. It's interestingly green. Oh, it's a type constructor, but it's just a function that takes two types and gives me another type. Okay. And basically, I've decided that mapping from key to value is just a list of pairs of key and value. So where was I using that? Oops. Right. So a mapping from field ID to value is just a list of pairs of field IDs and values. So suppose you've got some object, the typical object-oriented programming, the class ID might be animal, and the field ID might be eats. And the value, might be some other animal or something like that. And so, does that make sense? We can just sort of list out the fields and give the value that's in each field by just, so you might, an object, O1, object O1 equals,
you have a reference to this class and then a list of all fields.
right?
As a map in this case.
Stare at that for just a second. It's just like placing an order. So this here gives us a class ID. That's a field ID. Trust me, that's how you construct field IDs. Mm-hmm. And then I forget how you make values. It might be more involved than just a string. So that one might not actually type check. But that's an object. All right. So let's go through this just for fun. Okay, so we take addresses to be enumerable set adder and use the identifier A in adder to indicate an address. Okay, so basically when they said enumerable set, that means that there's just as many of these things as there are integers or natural numbers. So I said, well, okay, so then that's a data type where you can, given a natural number, you can make one of them. They have to be able to, you have to be able to put them in one-to-one correspondence with natural numbers. So that's how I represented enumerable. And then I was teaching it about equality, so never mind. And then set, I don't think I actually got right, but we'll skip over that. They talked about sets of something at some point. Oh, here we are. Values are either addresses or sets of addresses or null. So a value is either the value null, a value made it out of an address, or a set of addresses. And the set of address stuff, I don't think I got it right yet, but I haven't used it yet, so it doesn't really matter.
Can I ask you about this value? Is this like everything that you need, or this is the place where you want to extend it with another primitive types, like something that you will have from hardware, or some kind of low level types?
I don't know. I'm just trying to transcribe the paper as written.
Okay.
So they said null or address or P of address, and so I said null or address or P of address.
I see.
And by the way, if you've ever seen the union doodad, it's a disjoint union or whatever, but that's a lot like the pipe operator or the pipe syntax. Okay, continuations are either statements or a nested call thing. So there's two ways to make continuations. Frames consists of a code stub, and it turns out reading the paper by code stub is the same thing as continuations. So a frame is just a pair of a continuation and a mapping from identifiers to values. They meant variable identifiers. You learn by reading more of the paper. Okay. Then I'm going to probably not explain this slowly, but there's these things called interfaces. Yeah, this simplified life for me. Okay, so the lookup function, they'll do things like, okay, so we know how to look things up in a mapping from variables to value, but then they'll say, okay, we want to look up X in such and such a frame. And they really meant they want to look up X in this part of the frame. And so I sort of generalized this. And so I said, well, if you want to find the variables in a frame, it's the same as the variables in this part. And so this is like type classes in Haskell. So var env is an interface that takes two types, and you in order to say something has this interface, you have to define one function from the A type to the list of keys, the list of K. And that's premised on, this was the thing that was hardest for me to learn in Haskell, is what the heck is this rocket thing doing here? Basically saying all of this is constrained by
this K is not any type. It must have functions defined in DECIC.
Right, right. So DECIC is another interface, and saying, okay, so it basically says that K is decidably equal. That is, given two Ks, I can always tell you whether they're equal or not, and I have to give you a proof. DECIC either gives you yes and a proof that they're equal, or no and a proof that they're not equal. And you would think, well, wait a minute, aren't all types like that? Well, no, functions from natural numbers to natural numbers are not like that. It's not the case that I can always tell you whether these two functions compute the same answers given the same inputs. That's the halting problem. You can't prove in the general case for any two functions whether they always compute the same outputs for the same inputs. So not all types are DecEq, but many of them are.
So this says that you need to be able to decide for k, is it for two k's are they equal? Right.
Right. Right. And clearly, if I'm going to look something up in a mapping, I need to be able to go, oh, is this the right key? 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 So I have to be able to decide whether two keys are the same or not. Okay. All right. So this tells you where to find the variables in a frame. I don't think I use this implicit thing anymore. I'm going to skip over that. Okay. And then this I'm still maybe struggling with a little bit. Basically, a stack is a sequence of frames, but it's not allowed to be empty. So if they don't say, you know, it's either empty or one plus another one.
So it's like a semi-group and not monad.
I guess so. But basically, there's a way to say non-empty list using the list stuff, but I just went back to first principles and I said, well, a stack is either one thing, one frame, or it's constructed from a frame and a stack. I'm going to go over lists real quick.
I remember last time you explained you don't have a constructor for like a zero frame.
Right, right.
So,
but I'm going to do lists real quick because they're so fun. Let's call them sequence now. There's a thing called list in the standard library, so I'm not going to reuse that name. And you can make sequences out of anything. And the first way you can make a sequence is by not giving any of them. And the second way you can do it is, is by giving me one of these and a sequence of them, and that's a sequence. We'll see what the computer thinks of that. It thinks I'm happy. Okay. All right. The computer is okay with that, but it says, well, you haven't told me what Dan's favorite flavors are. I don't like any flavors. That's one way to do it. Okay. Another way to do it is I really struggle to spell chocolate, don't I? I think it has autocomplete, but I haven't learned how to use it. Chocolate. Okay. So my favorite flavors are chocolate and nothing else.
And you can also use a list syntax, right? Because
right.
you're using the codes.
So the people that make these programming languages have been slightly nice to us.
Or you don't have to say this, right? You can, because you're using nil and cons, you can use syntax.
Oh, maybe that. But, okay, so that might be another level of magic or something. But nil is often written this way, and in fact, yeah, Idris knows that they're the same thing, and I forget which mechanism they use to know that those are the same thing.
Just by calling your constructors nil and cons. Right,
but is this part of the parser, or did they also have a sequence, a syntactic sort of macro thingy? Anyway, so the other thing you can do is write chocolate.
What?
Did I misspell it? Chocolate?
No. But why doesn't know?
I think I have to call
Maybe.
it that.
Okay.
Yeah. And remember, we can make up our own symbols, right? Okay, so now I can write this. Okay, Gary's brow is not too scrunchy. I can also write that. So if I put chocolate on the front of the list, that's the same thing as the list consisting of just chocolate. I can put strawberry in the front of that, or vanilla. And that's the same thing as, let's see, vanilla, comma, chocolate. Let's see.
And this is nice. It prints you in, you know, in this nice syntax.
Right. Okay, so we have this nice list syntax, but they're not magic, right? They're just, it's just a data type made out of two constructors.
Yeah.
We've already learned everything there is to know about programming. There's occasionally nice ways to write things, but we already know everything about how to program. Okay. Okay, but in this case, the sequences have to have at least one thing in them, so I don't have a nil constructor here. There's a one constructor and a many constructor, or a one more constructor. Okay. And then if you want to find the variables in a stack, it's the same as the variables in the frames. This says if it's just one frame, then go find the variables in the one frame. And if it's a phi, that's a phi, or a phi, and this is a phi and psi or something. Anyway, if it's phi on the front of a list of the things, then look in the vars and then concatenate with the list of the. Okay. And then again, I think I'm not using the implicit stuff anymore because once I'd used the type classes, I didn't have to do that. Okay, and then you can concatenate stacks. And this is a typical recursive definition. If I want to concatenate one F on the front of B's, it's just F on the front of B's. And if I want to concatenate a, non-trivial stack on the front of the thing, then I just take the F, concatenate with, and then you recursively call our function. All right. Let's have a little bit of fun here. And let's say inventory. Take a sequence. Supposed to tell me that that's not, it's got red. I forget why it's not doing what it usually does for you're not done yet, but we're pretty clear on that. Control C, Control M. I've forgotten the case of X colon Y. And suppose I said chocolate. Oh, and can I get this thing to tell me that? Okay, so X is a flavor and Y is a sequence of flavors. And we have to come up with a sequence of flavors, okay? And so I suppose I said, well, I've got a sequence of flavors and I know that I can put chocolate on the front, but I can't spell chocolate, so let's go vanilla. So let's say that if I'm taking the inventory of a non-empty list, I put vanilla on the front of the rest of the list. All right, and let's see what the computer thinks of that. Oh, it thinks that's okay. Oh, now I know what I mean. Okay, suppose if I want to get the inventory of the empty, I don't have any flavors, and so I want to take inventory. I don't know any. Okay, and so inventory is sort of my what I'm going to order next week or something like that. Anyway, suppose I've got some flavor and then some more flavors, and I say in the inventory in that case is vanilla stuck on the front of X on the front of Y. And if I ask the computer about that. Oops. That confuses me.
I'm not completely sure what are you expecting.
Okay. Oh, now I remember what I was going to do. Okay. If I got it.
But X is just one flavor.
Well, let's suppose I did this. I was, late at night, and I got a little sloppy or something, and I said, yeah, for an empty inventory, next week's order is going to be nothing. But if I have some stuff, then I'm going to order vanilla plus whatever the inventory of X and Y is. Okay.
You must put parentheses.
Oh, right.
Okay.
Okay, so now it's okay in some ways, but I've got some inventory of, let's suppose that's strawberry. I just have strawberry and vanilla. And this says, okay, add vanilla and then call inventory of strawberry. And then call inventory of strawberry. And then call inventory of strawberry. And then call inventory. Well, you're not making any progress here. Right? So I haven't actually told the computer how to compute the answer there. I've just told it this kind of loop, I've said, how long is a piece of string? Well, it's as long as a piece of string. Well, how long is a piece of string? Well, it's as long as a piece of string. So this is not an effective definition. It doesn't actually, it's not guaranteed to terminate, to produce an answer all the time. And in most programming languages, if you wrote a function like this, the compiler would be just happy and you'd run your program and then your program would get stuck. And it would just sit there going loop, 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 loop. But Idris can tell you at compile time whether you made that kind of bug.
And you put this vanilla in front to just have something that is not completely just a regular loop, right?
Yeah. So what I have to do is I have to make sure that whenever I do a recursive call, the recursive call is on something smaller than what I had on this side. And that's the way I make progress. It's like the way you add two numbers in Idris is if you want to add 3 plus 2, it goes, oh, gee, I'm not really sure. But I know that 3 is one more than 2. So I'll take 1 and stick it over here, and then I'll add 2 plus 2. And I don't really know how to do that, but I know that 2 is 1 plus 1. So I'll take 1 and stick it over there and add 1 plus 2. And now I know that 1 plus 2 is 1 more than 2, which is 3. Okay, and then I had a 1 that I was keeping in my pocket, so I'll put that back on. So that's 4, and then I had 1 that I was keeping in my pocket, so I'll put that back on as 5. So 3 plus 2 must be 5.
So Idris knows this by knowing the length of the list. Or
more than the
now,
length of the list, it's this structure, it's the syntactic stare at it size of the term. So
although you're in this situation, but you are removing X and adding another, or
right. But if I did this, if that was inside the recursive call, I might be in trouble.
Yeah,
right?
Yeah, this is like exactly.
But as long as the part in the recursive call is smaller, then I'm cool. So Idris doesn't know lengths of lists. It only knows these things up here, constructing data and taking it apart. All right. Oh, so that was a recursive definition, right? Runtime configurations, sigma, are pairs of stacks and heaps. So configuration is a pair of stack and heap. All right, then we're going to get into interpretations. We first define lookup on fields and classes where A is an address and fields identifier. And they're saying, well, what's X? Oh, X is an identifier. It's like a very, let's see. XAF, no, I can't. Let's see what I'm going to do here.
Sorry, Dan. You said that you are writing a paper about implementing programming language, or you are reading a paper?
Reading.
Reading. Can you link this paper or something? Or?
I'm not supposed to distribute the paper. So
okay, sorry.
Right. So I guess X is this lookup function. It must have been some symbol that I had trouble. It was some weird Unicode thing that doesn't come across or whatever. But to look up a field identifier at some address,
What is this strange character?
oh, this is chai. This is the heap. It's saying if you want to look up a field at an address in the heap. So in the heap, we've got a heap. Sorry, where's a heap? A heap is a mapping of addresses to objects, right? And objects have fields in them, right? So this is basically saying if you want to look up in a heap a field of an object at some address, it's saying, okay, that's field map AF if when you look up A in the heap, you get an object with this field map. Okay, and so the way I just define that is this lookup doodad, and I'm going to use, where they write like M of key, I think I already said this someplace. Right. Where the paper writes M at K, we write M dot at K. And then since M at K may be undefined, we return a maybe V. And then sometimes they write F of M of K, but M at K might be undefined, so we have to use other stuff like do notation or whatever. Devo, it's okay. It's okay.
Oh, sorry. Oh, this dot at is for this key value list, and dot at is lookup for a heap.
Yes.
It's very similar. Okay.
Yes. Okay, so you want to look up the pair of an address and a field ID in a heap, and you may get a value. Okay. And
oh, with address you will find the object, and with field you will find field inside this object.
I think so. Let me just go through it a little bit here. So when they write their chai that way, I write the chai this way. So chai at A and F. So do notation I'm not going to go over, but it just expands to function application and stuff. But you basically look up the address in the heap, and that's going to give you a maybe. And the do notation here says that if the maybe is a just, then it'll bind to this pair. And we took the pair apart and pattern matched it against the field map here. And then we take F and we look it up in the field map. And if we win, we get a value. And in that case, our answer is pure V or just V. So that says the same thing as that, I think. Follow me, Tom?
Do you need to prove that this field it really belongs to this class?
This definition is without respect to the class ID. I put a wildcard for the class ID because when you look this thing up, it doesn't care what the class is.
Yeah, class is like just a grouping of fields.
Right. Okay, they do have a thing that says, if I want to look up the class of an address, is the class of an address in a heap is see if looking up the address in the heap gives me a pair where the first item is C. So in this case, I do care what C is.
Excellent.
All right. Right. So the interesting thing bit here is kind of how to interpret expressions given a configuration, a heap and a stack. So we're getting there. We're putting together little tinker toys of how to do it so far. So we got field lookup in a heap and class lookup in a heap. And now we're getting to, so then I had all these troubles with interpretation until I remembered this bit about interfaces like Haskell type classes. And so I've got an interface called interpretation context or interp context.
I seen you deleted interp function, and right, you replaced it with this interface. Yeah,
I had a different way of doing it a week or so ago that was a real pain, and this turned out to be a lot nicer. And so they use this syntax, sort of. This is the interpretation of X in phi. And I don't know how to use like these kind of things in Idris. Idris is not very friendly about non-ASCII stuff. He made a decision about that because people went too crazy with it in Agda, and you can't Google the things. And it's bad enough that you can use these things. Anyway, so when he writes X in those kind of brackets with a subscript phi, I write X /phi. Okay.
Oh, these brackets, right?
Okay. And so this says that if you're telling me that T and A make an interpretation context, you have to tell me how to interpret T in A, and it gives me back a maybe value. Because sometimes when you look up a variable in a frame, the variable's not defined, and so it's you get nothing instead of just. Okay. So a variable in a frame, phi, is that syntax makes for an interpretation context, and to interpret X in phi, you just look up X in phi.
Let's see.
Now he's got X.F in phi and chai. Is V if blah, 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 blah. It's kind of straightforward. It's basically saying you want to interpret, in JavaScript, you might write animal.cousin, right? And what that means is take animal look it up in the heap. Go find that object. No, wait. Oh, it means take the word animal, look it up in the current frame, and then you'll find an address. And you look that address up in the heap, and you'll find an object, and then you look up cousin in that object. Okay? Okay, and so what I'm saying is that, and x.f, when he writes x.f, I write x.f, and I call it a field access. So we can interpret a field access in a frame and a heap by doing, okay, so x.f in phi and chi is the locals of phi at x. Okay, if def, and then take the resulting address, and then if the address is one of these val adder things, because remember it could be null. There's different kinds of values that you can get up when you look things up in the heap. But if it's one of these values, and that was implicit in their definition. Anyway, so then we're going to look up A in the heap, and if we win, we're going to look up F in the field map. I didn't use do notation in this one. I could have. Probably would have been more clear with do notation. I might rewrite it that way as a little exercise here. And then if def is a little function that I made up here. It's just a locally defined function. You've got a maybe A and a functions from A to maybe B, and you get them back a maybe B. So if def of nothing and whatever function is nothing, and if def of just F and a function is F applied to that thingy.
I think that your if def is exactly the bind melodic.
Oh, it's bind?
Yeah, it's, FA to A, FB to FB.
So I could use do notation for this.
Maybe you can just replace if def with bind infix. And it's with two arrows. Yeah. This should work, right? No?
It's checking. It's a non-trivial size thing, so it takes a little while to compile.
Oh, it's still checking. Oh.
You're right, though. We win.
Oh.
Oh, that's later.
What's happened?
There's something later in the program that I haven't finished defining.
Oh, okay. Nice.
But since I could use the bind there, I probably could use do notation. Anyway. And then these shorthands. Go ahead.
Yeah. So what we achieved, what we replaced with bind, operation that was doing what? Oh, this was a bind on maybe. Thanks. Okay.
Bind on maybe. Yeah.
So this explicit bind that we have written was easier for Idris than using built-in bind, or the type checking is just long, whatever you do.
Oh, the type checking is long, whatever you do.
Okay.
I get this is a sort of longish program, so.
Cool.
I mean, that was compiling basically. Right. Yeah. I mean, I just replaced ifdef with bind because if I gave this to other people familiar with Idris or Haskell, then they could easily recognize that syntax.
Sure.
Whereas they'd have to read the definition of an ifdef and do what Thomas Loft did. Oh yeah, I know what that is. Why'd you spell it out so long? Okay.
It would be nice that Idris tells you, I understand this function. You already have it, You don't have to write it.
You can do type lookup.
Yeah.
You can do type lookup.
Yeah, but he needs to know more, right? To say this is completely the same as maybe bind. Maybe you did something strange in your function. So
hold on, let's see. So the type was this, right?
yeah.
Right. So this is, you're right, that this type is not generic enough, but we'll probably find something. So search for type. Yeah, there it is.
Yeah. You could say so.
It's got a thing called maybe bind.
Yeah.
And if you generalize that, you get this. And there's a thing called choice map that also has that type. Yeah. So if you've got some puzzle that, you know, a type is like a blank in a puzzle, right? And if you want to say what goes here, you can just ask, you know, is there anything in the standard library of that type, or is there anything defined in my scope of that type? And you know, the thing will just look it up for you.
Yeah.
Oh yeah,
or maybe in any other library on the internet, right?
Yeah. Okay. And they use this shorthand. So where they write phi there, remember that's a list of things. So, the shorthand, if you want to do x in phi, psi, chi, then it's really just x in phi. I'm trying to remember which way is the shorthand. That's weird. This is longer than that. Anyway, to interpret. Oh yeah, now I remember, because they're going to talk a lot about interpreting something in a configuration. So it's basically saying to interpret something in a configuration, take the top frame in the stack and look it up there. And that's to interpret a variable identifier, and then if I want to interpret field access, similarly. Now this I'm not sure about, because
frames are like execution steps, or because I'm wondering what are nested calls inside frames.
Well, right, a sequence, a stack of frames is when you've got, you know, a call pending, right? You're several layers deep in the call stack. I think this is not quite right. I think it should be.
Oh, so nested call is like a standard. Yeah, you're creating a new stack, right? Because you have nested calls. Okay.
What was I here? I screwed up trying to put. Okay. Yeah, that was kind of weird. Where's it? They only wrote out the case of many, but I think that they actually sort of meant that psi can be empty. So I think they were not quite precise in their notation there, but anyway. Well, I think their notation basically means a non-empty list. So.
Okay.
And I don't know why I didn't do anything with those. Okay. So assuming that phi is stub and var map, we use phi.continuation to mean the stub. That's where I learned that stub was the same as continuation. So CONTN is just the way to get the first thing out of a frame. All right, then they're gonna define updating the continuation. So update stub takes a continuation and sort of a replacement. Right, continuation stuff equals. Locals fee. Oh.
So you're not using cont.
This would be another way to write it. I think.
But now you're not using frame.
Hold on. Yeah. Frame is a continuation in a variable map. Okay, sorry, I'm not using what?
The first argument.
Well, I'm using stub. Oh, wait. Oh, sorry. Uh-oh, I've got some work in progress here, don't I? Where did I... Stub prime and var map.
And what is the idea? To just replace a continuation with some other continuation. This is the only thing, right?
Yeah, you're just replacing the continuation. What's going on here? Assuming A of...
But why are you accepting two continuations? Can you just accept this one that you want to replace?
Fee with continuation goes to stub for updating the stub. Assuming a value V, what's that? Take it easy, Deagle. I'm confused. Hold on. I'm going to put it back.
But you don't want to discard this inner continuation that you already have, right? in a frame, or...
Right. So if this thing is stub and var map, where does fee come in? What? Oh, fee is this. You got too many arguments here.
Oh, okay.
And the locals is the var map.
Okay.
Yeah, that's what they said here.
Yeah.
Yeah, if you want to update the stub of a stub and a var map using stub prime, then stick stub prime in there. That's all they said.
Yeah.
Okay. Now this one, you want to update the variable map in a frame. You want to assign x to v in the frame. So you stick xv on the front of the mapping. Okay, so this prepend same was a lemma I had to use to prove something, which I'm going to hope to get to pretty soon. probably shouldn't go up too much longer. Okay, so heaped update is another kind of thing. We're going to take the heap and at some address, we're going to put some object. Oh no, we're gonna update the field of an object there. Yeah, because it's possible that the address we're looking for is just not in the heap, so that's why. Okay. Map is another thing I made up. New stack is another thing I made up. This is kind of fun.
Yeah, this is the most interesting.
Yeah, I'm actually going to skip over that because it's not the part I was struggling with. This is the actual definition of how you execute a step in the program.
Yeah.
Well, how you do a method call.
Yeah, and this is the only way to make reductions, right? In this program.
Yeah.
I mean, you don't have any other functions, right?
I'd have to look it up in the paper, but I think there weren't any others. Yeah, it's basically if there's all these preconditions, then this reduces to that.
This looks very nice. So this is like the whole execution, right?
Yeah, right
here.
Yeah, if you've got a function of this type and you apply it to this many arguments and you look them all up in the heap and blah 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 blah, but then you get the next thing, right?
I like it.
Devo, you're gonna have to wait. You're just gonna have to wait a little bit. Yeah, my dogs are. He's decreasing patience here. Come on, Papa, just a little bit. Okay. And then there's basically the transitive closure of that is the many steps. And I'm hoping to actually prove stuff about all this stuff. Okay. So so they have all these definitions, right? But the first theorem they have, this lemma A1, is that if one configuration is an extension of another, then it preserves interpretations of identifiers and some other things. And here's what let's see, the definition of extending a configuration. The relation, that thingy, is defined on runtime configurations as follows. Take configurations sigma, sigma prime, and sigma double prime, frame, phi, stack, psi, and psi prime, heap chi, address A, free in X, free in chi, value V, and object O, and define sigma extends sigma prime as the smallest relationship such that it's reflexive, so every configuration extends itself. And then if you update if you add a variable mapping, that extends a frame. If you put more stack stuff on the end, that extends a frame. If you update the heap, that extends a frame. And frame extension is transitive. So let's spell this out in Idris.
Okay, can you just say what does it mean to extend the frame? Did you say extend the frame?
I meant extend the configuration.
Okay.
And it means just what they said here. So okay. And whenever there's he calls it a relation here, sometimes you'll see judgment or whatever. But whenever there's a thing where you can just say, it is so, which kind of like a judgment, like wonderful. So that says that Bob is wonderful, right? That's kind of a judgment, or or cousin Bob Sue. That means that Bob is Sue's cousin or whatever. And you can also write that this way. Cousin Bob Sue. That's just sort of a judgment or whatever. Turns out that you represent these things as data types. Okay, so we've got a data type extension. Well, we've got a data type constructor extension. It takes two configurations and makes a type. and there's 5 constructors. The first one is that extension is reflexive, and that's all, just that symbol right there is all you need. It's kind of like the nil thingy or whatever, and that is a proof, or is a constructor for, that tells you that sigma is an extension of sigma. So that's the constructor for this case. I called it extension variable map, given a variable and a value and a frame and a stack and a heap, and a proof that X is free in phi, that is some term of type X free in phi, and I'm going to allow that to be an implicit argument, and I'm going to allow Idris to automatically find it when it can. Because a lot of times they just have these side conditions, and this is the convenient syntax for side conditions in Idris. Given all that, then ext varmap is tells you that update varmap is an extension of this other configuration. So that's kind of unpacking what they wrote here. You can extend the stack likewise, you can extend the heap, and then ext trans is easy to look at. If sig prime is an extension of sig double prime, and sig double prime is an extension of sig, then sig is an extension of, sig prime is an extension of sig. So if B goes to C and C goes to A, then B, wait a minute. It's if A goes to B and B goes to C, then A goes to C. Okay.
Yeah.
I don't know why they did it that way, but they did, right? Prime goes to double prime goes to no primes, then single prime goes to, all right. So that's just their definition spelled out in Idris, right? Okay.
This means you can combine 2 configurations, right? Like almost like two executions. You can combine.
I don't think it's combining them. It's just saying that this relation is transitive. It's like if you have 2 of these relationships, then you can conclude a third one.
Okay.
Yeah, you can combine these extension relations.
I mean, it reminded me on the graph definition for connect, I think. Right? You combine 2 graphs and you care about the variables, right? Are they the same?
Yeah.
Because you're saying variables must be different, right? Or,
yeah, I mean, what they said in the paper is that basically an extension has more information than the other one. Anyway.
Okay.
So whatever, they have this thing called extension, and now I think I understand what it is because I wrote it down and it type checks. But I won't really know if I'm right unless I can prove the same implications from it, right? Okay, so I had to use this ext define thing, and maybe we'll come back to that. Okay, so this lemma 1, if sigma prime extends sigma, then they've actually got 1, 2, 3, 4 consequence of this, and I've only done 1.5, and the 1 took me like 3 weeks.
Yeah.
Okay, so this says if sigma prime extends sigma, then if X is defined in sigma, then the interpretation of X in sigma prime is the same as the interpretation of X in sigma. Okay? So we'll write out this lemma, and this is lemma 1, A1 part A. This is the little A there, I guess. Okay, so usually you can just leave implicit things implicit, but if there was some kind of ambiguity, and so I had to tell it, that X is a variable ID. All right, so
so you want to prove one of the properties. You have two configurations.
Yep.
And now you want to prove something inside the configuration and say, you see, they're the same. And I have this proof of transitivity, which I can use to prove this.
Transitivity turns out to be an obligation here. We'll get to it soon here. This is saying if there is an interpretation of X in phi, then when you extend phi, the interpretation doesn't change. Okay. And we're just going to do things like a computer here. We're not going to really think about what they mean so much. They just said if sigma prime extends sigma. All right. If extension sigma prime sigma. Right. That's just the way we're using the notation. All right. Then if this thing is defined, and the way I've written that is if this thing is a just, and it's not empty. If is just this thingy, X in sigma, then X in sigma prime equals X in sigma. So that's our claim. That's our proposition. That's our type. So to prove this, we have to write a function of that type. We have to exhibit something of that type, and then we will have proved the claim. Okay. And this is going to be a little bit slow because this file is so big, but I'm going to just give you a flavor of what you do to do this. Okay. So I'm going to comment all that out. So I'll just follow my nose. I'll do Control C, Control A. No, sorry. Control C. Start. Control C, Control S. All it's doing is I screwed up something earlier. What did I do? Maybe I don't want to fix this. All right, let's just do the same thing, same game here. Control C, Control S. K-split. Oh.
Oh, but is it the frame a tuple? Maybe you just need to reverse the arguments.
Right. Well, let's just go do this anyway. All right, computer, start our definition for us. And then K-split this thing. I wanted to make it a pair. Yeah.
Okay.
And this is, we can name these whatever we want. They like, oh yeah. And then let's see if it'll automatically figure that out. Probably not, because it's got two choices. Yeah.
Nothing. Oh.
Let's see if that works. Yeah, okay. It's happier with that now. Okay, now we are... All right, so this stuff down here, I'm going to comment that stuff out. So that it doesn't get in the way. Oops. Oh. these things are documentation comments, and they're kind of significant to the parser. Okay. All right. So my type is syntactically okay. Now I say, follow your nose, computer. All right. And then what did I do here? Okay. So if sigma prime extends sigma, well, it does so in one of 5 ways, right? They're either related by that, or that, right? The extension is constructed somehow. So we'll k-split. All right. And
Dan, I'm not quite clear when you say case split. Can you explain that a little further? Is that of the continuations? One of the 5 continuations it could be. You break it down into different cases. Is that
yes,
it?
yes.
Okay.
So we've told this thing that there are 5 ways to construct an extension.
Just like no and sum.
Right.
Oh, okay. That's helpful. Thank you.
Right. And so we know that X is of type extension sig, or sig prime sig, so it's got to be one of those 5 things. So the computer says, okay, well, you just have to give me the answer in all 5 cases.
Okay, so and that's case extension, or
Case split is what they call it. Yeah.
Case split. Okay.
And they've taught editors how to do that sort of semi-automatically. Right?
Gotcha. Okay.
Usually some languages have like case switch or something like that.
Right.
Okay.
Or pattern matching.
Right. This is an alternative
okay.
syntax to a case statement.
Okay.
Okay. Now, in the case of reflexivity, if you have this REFL case here, that's basically saying that sigma extends sigma. In other words, these 2 guys are the same thing, which means that this is going to be we're trying to prove x in sig equals x in sig. Well, obviously it is. So the computer can probably figure that out for us. So we'll do auto here, and it did. And so I don't know if you've, but this will blow your mind, but equals is just a type. And you can think of it this way, or it's probably in the standard library if I looked it up or whatever. No, let's see. So equals, given any type, makes a type that can only be constructed one way. And that construction is called reflexivity. And it implicitly takes some x of type A. And it constructs x equals x. Sorry, this must be 2 arguments. In other words, equals XX. That's all there is to equals. It's not any kind of actual magic thing. It's just like chocolate, vanilla, and strawberry. Equals is a type with 1 constructor. REFL. And basically what it's saying is that REFL A or REFL X just means X equals X. Obviously, that's pretty straightforward. Okay, so REFL is a proof that this equals this, and the implicit X in this case. So it's got this implicit X argument, So I could write x equals, I think.
You mean what? Why? Or I wanted to ask you about why.
Y is in the question, or Y is in this thing here?
What is why?
Y is this bit here. Oh, sorry. Y is the if part over here. So our function has one argument there, and then it effectively has another argument there, and this is what then the result is here. So it's if extension sig, and is just this, then we got it here. And I've put extra parentheses here for no good reason.
Okay. Yeah. Okay.
And this isn't working, and I don't understand why, so I'm going to skip over that. But there's an implicit argument to REFL, which is what is it that's equal to itself? And so the computer has figured that out. All right, so we won and since we're not using Y, it's traditional to sort of do that. And then this, in the case where we're taking in a configuration and extending the variable map, it took me forever to prove that case. What did I do? All right, so first of all, I've got this implicit argument, and I'm actually going to use it this time. So I'm going to grab it. And the x that's implicit here, the x that we're looking up, the x that we're interpreting is not necessarily the x that we're extending this thing. So I did this, because otherwise Idris will say, wait a minute, those aren't necessarily the same thing. You can't use x twice on the left-hand side without more magic. When you're pattern matching, if you use a thing twice, it's not fair. So what else did I do here? Then I broke, so phi is, I'll k-split that. Wow, that was bizarro. But it did make pair. So this thing is a pair of two things, not x and y. So a frame is a continuation in a variable map. And then I left sign chi alone. And then there's this auto argument up here. Remember they said it says A, free, and X. I actually had to write to the author of the paper and discovered that they actually meant to say X is free and phi. So that's why I have this X is free and phi here, because that was something that the author of the paper told me.
And what do you say auto is?
Auto just means that Idris will, you can expect auto to automatically find that argument sometime. I'm not really sure. We're not going to use the auto-ness of it in any case.
Okay.
And then
Is this auto similar like in Coq, where you write like strategy? So you could, so Coq tries to figure out and prove stuff by itself?
Probably. I don't really know. I'm a little bit monkey see, monkey do. It seemed like the kind. I had seen somebody else use auto for something similar, and so I did the same thing.
Sure.
I'm going to talk about how free in is not magic. So free in is a function that takes, well, it's a type constructor, it's a function, whatever. You give it a key and environment or map or whatever. So it's like a judgment. we're saying that key is free in E. And this only makes sense under the constraint that the type K is decidedly equal and that we know how to get the variables out of the environment. Okay. And so the definition of key is free in env is not, the element is not in the variables of the environment. An element has two constructors, either the thing is the first in the list or it's later in the list. And that's part of the standard library, element. So free in is not magic. In a lot of situations, free in is magic. They just sort of say, everybody knows what that means. But in all this Idris stuff, it's not magic. It's just regular. We already know everything about how to do computing. So where are we? We're down here. Oh, right. So we had that implicit argument, and I'm going to make it explicit. And then this argument here was hard to remember what it was. And it's basically, the Y is saying that thing is defined, so I'm going to call it defined.
Can you make this argument implicit? Because I see it as like a proof that you have X defined, right?
Yeah.
It only says, right, this may be, I'm only interested if this maybe returns array, right?
I'm going to prefer not to do that, but I could. But yes, you're right. I could make that an implicit argument. But I'm going to leave it an explicit positional argument for now. But I'm going to call it defined. Okay. And then let's see where we are. So far, all I've done is follow my nose. I've just asked the computer to k-split, and it did that automatically. And this was one of the cases. And then it should have been able to do this k-split of turning a pair into these two things, but it went nutso when I asked it to do that. That was a bug somewhere, probably. But anyway, I just rewrote this pair as the two parts, and I changed the variable names to things that are more helpful for me. This time I made a implicit variable explicit. And I renamed this variable to something that's a little bit helpful for me. And then I just asked the computer, where are we? It's saying, okay, so you've got a var ID x and a var ID x prime, and you've got some value v, and you've got a continuation. Var map is just a list of var ID value things. That's what we told it a mapping is. Psi is a stack. Chi is, a heap that turns into that. X free is of that type, and defined is of this type. And we're supposed to prove it is sort of expanded out the definition of interpretation here. We're supposed to prove that that's equal to that. So it's kind of, it gets a little bit cloudy to read things here. But maybe Tomislav, if you're following?
Yeah. Well, why do you see error on the first line?
Sorry?
Why do you see error in the first line? When you define
this red thing here?
Yeah. This is not an error, right?
Right. I don't know why that's red at this point.
Okay. Just really confusing. Okay.
Yeah. I'm not sure what's going on there. Okay, so the next thing I did, I'm just reading my own code down here. There's this dependent pattern matching, which is a little bit like, I'm taking some configuration, and I've got this map of variables to values and stuff, and I'm updating it. And it could be that x and x prime are the same variable, or they could be that they're different. So one of the things I can do is and there might have been a way to get the computer to do that for me, but oh, actually there is. Okay. So the DESEQ constraint told me that there wasn't a constraint. It's just the way var IDs are constructed. Earlier, I sort of established that var IDs are DESEQ. You can always tell them apart. So I get to call this function, and it gives me either a proof that they're equal or a proof that they're not equal. So the proof that they're equal is a proof that x equals x prime. Okay? And the proof that they're not equal...
This is REFL, right? Proof equal is REFL. Proof equal is a REFL constructor.
That's right. There's only one way to construct this type. So PFEQ must be REFL with some argument of x. So that you can do. And then there's this. You can get it. You can do the with rule. It's supposed to do a certain amount of stuff. I just ask it to do the with rule for me.
Yeah. Oh.
This with rule is something like there's a special command for this, right?
Yeah, I did Control-C, Control-W or whatever.
Cool, thanks.
And then you put DESEQ x prime here. And then I'm going to ask the computer how I'm doing. So the interesting thing is, so that's where the proof that they're equals goes. So I didn't use this when I wrote the code because I just discovered this last night. But now that I have a proof that they're equal, I can do that. Since I have a proof that they're equal, I can use the x twice in the pattern, I think. Oh, bummer. Okay. I think there's a way to do that, but I'm not going to work it out right now. So what did I do next? Yeah, I'm using this with dependent pattern matching, but I'm not sure why, frankly. Let's skip over that.
Can you express everything just with the case? I mean, is it possible? They are not the same, right? Because in this bug that you show, the case is not working, but with is working. So they are not the same, definitely.
Right. Yeah. Okay. So. If they're not equal, somehow this case was really easy. So let's see why that is here. Okay.
What do you want to say when they are not equal? They should not be possible, right? I mean, or
why is it not possible?
I'm looking at a return type which must be REFL, and you must return a REFL, right?
Right.
In all of these cases, right? And for this proof of not equal, I'm not sure.
Well, let's actually look at how this works because it's kind of interesting. This function gives us back a deck, and deck has two constructors, so there they are. And in the no case, we're down here looking at ABC, and these are the things we know. The proof that they're not equal goes from, if they were equal, then I have something of a type that doesn't have anything in it. So that's how you say not equal.
This is interesting.
Yeah.
This is like negation of equal.
Yeah.
Makes sense.
How did it do this? Somehow it decided that interpreting X in sigma prime is just looking at X in var map. Why did it do that? I don't remember. I think, let's see. X is free, which tells us that if X were in the variables of var map, then that would be crazy talk. Oh, and this is...
X is not free, right?
Right. But how did it figure that out from just what we've got here? Well, okay, so I think what it did was it expanded this definition and then somehow reduced it down to this. I'd have to think through that. In any case, you know, proving that var map at X equals var map at X is not real hard. The computer can do that for us. All right, and then if in the case that yes, okay. What did I do here? So there's this replace function that allows you to take a proof of equality and do substitution. And this is how you spell out what it is you're substituting. Well, no, this is, the thing that I'm substituting for is T, and to make the substitution into the whole thing, this sort of tells us that here's where the substitution fits inside of this defined thing. So the defined thing is just blah, blah, blah. And I'm basically claiming that looking up X in sigma is T at var map. Let's see. My proof of equality is that X is equal to X prime. So that should be able to allow me to say that X prime slash sig is a just as well. And then X prime bound Defined has key is a little bit fun. I'm going to go look at that one real quick. So this is basically saying if you win when you look up key in an environment, then key must be in the variables of the environment.
Okay.
So your environment is it's a list of key value pairs, and if it's empty, there's no way to pattern match, and so you get to use this impossible doodad. The elem thing doesn't have any constructors where this part here is empty, and so you get to use this impossible thing. And then if the environment is some key map to some variable, and then some more environment stuff, then either the keys are equal or not, and if they're equal, then the thing must be the front of the list, and if they're not equal, then blah, 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 blah. It's really kind of interesting. But I'm not going to go into it just now. I basically asked the computer to show me what's the current bindings and kind of followed my nose. Absurd is kind of interesting. It's like if you have an element of the void type, then you can generate an element of any type. That's what absurd does. So in other words, H4 is some contradiction. It says is just nothing. Well, that's not the case, right? Nothing is not just. That's silliness. And so if you've got silliness, then you can trade that for anything.
Yeah.
So it's like a rule that from false you can prove whatever.
Right. Ex false nihilo or whatever that was called. I forget.
Yeah.
Yeah. If you can lose information in black hole, whatever.
Not a Terminator. I forget. Oh. Right.
So you mentioned substitution. So in this case, you detect that you have the same name for the same name in this other environment.
Yeah.
Configuration.
Yeah.
And you want to prove that if you can change the name to be free, this is the same also.
Right. In other words, one of our conditions was that X is free. And so if we discovered that these two things are equal, then that's silly because earlier you told me it was free and so it wasn't there. And so that's absurd.
Oh, at the end you are proving this is absurd.
Right.
Okay.
It's, yeah. If you take the X free proof and apply it to the case that X prime is bound, X and X prime are the same thing, and so you've just told me silliness.
Okay.
And similarly, somehow the stack and heap cases were really easy. And the transitive case was really hard. I had to do this ext define thing. What was that? If sigma prime extends sigma and X is defined in sigma, then X is defined in sigma prime. And I had to do all this monkeying around to get it to do that. And after that, the transitive thing was really easy. So if I've got 2 extends 1 and 0 extends 2. And those are the names of the implicit arguments, and proof that X is defined in 0, 1. Then we're going to recursively apply our lemma to ext20, and that's going to prove that the extensions are the same in sigma prime and sigma double prime. And then we need to know that, one of the premises here is that it's defined. This is just the thing here. And to get that premise, I had to go through all that monkeyness above. And then once I got that, then I can apply our thing recursively to ext1, 2, and the d20 define 20. And then where's trans? What the heck is trans? Oh, trans is in the standard library. Trans is if A is equal to B and B is equal to C, then A is equal to C. So EQ12 is a proof that 1 is equal to 2, and EQ20 is a proof that 2 is equal to 0. So this gives us a proof that 1 is equal to the 1 case is equal to the 0 case, which is what we were after.
Nice. So, yeah.
I'm gonna. That was a good fix. That was a good fix. That was a good fix. I think that was a good fix. And this is white space. Oh, this is in progress. Oh, crap. Oh, and right, this is the stuff I'm working on next. So all of that, getting all that to work in all 5 cases there took me a long time.
Yeah, not easy stuff.
And that's the first of 5 bullets in this lemma A1. So now I've got all these other things to prove too. And I was kind of following my notes through this one. And it's kind of the same thing. Is it? Yeah. Except where up here we were just dealing with where are we? Oh yeah, the interpretation of a variable in a configuration, X in sig. Down here we're dealing with a field lookup in a configuration. And you might remember that a field lookup had like 3 steps to it, roughly.
Yeah.
So it's kind of like take all that stuff and multiply it by 3.
So in a sense, the first case is proving that you have directly on the stack, you have reference to the variable. And now you have indirection. You must first find the address, like a reference. Right. Then you need to find value. And
right.
But when you do this, you know, you're very close to, for example, do some proving on C# or Java, right? Yeah, yeah. This language, this Loo language, is very much like C# or Java or JavaScript or something like that. Yeah. When you are on a halfway, you know, just. I think Loo is language object oriented. So the short version is we went from, there's only about 3 mechanisms for computing to like the edge of computer science. Yeah.
So Idris,
yeah, I like your introduction for very, very simple cases to
yeah.
the whole thing. Yeah.
And there's a lot of steps in between, but none of them are magic. And you just sort of have to run them through your brain fast enough until you get intuitions about doing it. So there's certain things that I know how to do in Idris now where it's straightforward for me to do it. And you can imagine the developer of Idris going, man, that's really easy. I'm going to teach the computer to do that. So then now it's one keystroke to do that thing, you know.
Yeah, someone who learned Idris like the first language, you know. He was just explaining, how can you not understand? This is like normal.
Right. Yeah. So that's certainly one of the thoughts I had after I understood Haskell. It's like, wait a minute, why did you bother me with C and assembly and Java and all that crap? Hey, you're polluting my brain with all kinds of noise. Just let me use Haskell and compute, would you?
Yeah. I mean, it's strange to see in a function that you say is just, right? And then you also write the function like the lookup, and you're saying, I have the lookup. This argument is a lookup, and it will definitely have a value.
Right.
This is like super strange.
On the other hand, there's no magic.
Yeah. It is magic. It's executed on the compile time, right?
Right, yeah. Well, that's only because you're used to all these other languages that divide
distinction, right? Between these.
They divide up compile time and evaluation time. And in Idris, it's like, we're not gonna make those weird distinctions.
Yeah.
Just everything's just sort of ordering ice cream.
Yeah. But I see this in a sense that you don't have this distinction. You only have program that will stop in this moment, right? Because you don't have any other code to execute.
Right.
But this is not the end of the compilation or execution. This is just you wrote the code until this level, and then you know.
Do you have thoughts about what is, because you translate something into Idris to understand this or validate this paper, but do you recommend something like super easy to validate or understand?
There's a bunch of so I would definitely recommend the book. And the book goes over a bunch of stuff about, there's this vector type. Normally we just have a list where it's either nil or cons, right? And they have a vector of n of things where n is a natural number. And so like if you want to do zip, the lists have to be the same length, and you can tell that compile time and stuff like that. So they do a lot of stuff with vectors that's like, wow, that looks hard, and then it turns out to be really easy, or that looks easy, and then it turns out to be hard, but it's not too hard. Where's the book?
You're probably saying about type-driven development with Idris, right? Okay. Yeah, I know the vector example from lectures from Edwin Bradley from Oregon Summer School.
I guess I would just recommend you take any paper either well within your understanding or on the edge of your understanding and try this exercise.
Yeah. Good point. Do you use any other programming languages except for Idris?
Oh, sure. I mean, I write Python and stuff, you know.
Okay. So do you think that understanding Idris influenced the way you write Python, for example?
Definitely. Mostly it took me a long time. It took me like 3 runs at it, and the 3rd run was like 18 months to get Haskell. But it was mostly just unpolluting my brain. Right? I mean, in Java, you write x equals x plus 1. Every high school student knows this is nonsense. X doesn't equal X plus 1. Stop that.
Immutability is change everything. But Haskell do this for you, I believe.
Yeah,
No?
right. So it was when the light went off with Haskell, there was something about the invisible syntax that it was hard for me. Oh, you know what it was? I had a couple runs at Haskell, and I didn't get it. And then I learned Scala. And Martin Odursky's Scala book was really good. And it was like, oh, that's how Haskell works. If you actually put the punctuation in there, I can see what's going on.
Yeah.
Right.
Yeah.
But once you understand what's going on, the punctuation is noise and you don't want to see it anymore. But when they'd write FAB, and I'm like, well, which way does it go? Does it F of A and then B, or F of A and then B? And I don't know what
Yeah.
Sometimes you put a $sign in there, and I don't know why, and you put this rocket arrow, the solid arrow and 2 colons, and sometimes 1 colon. I just don't get it. But
Yeah.
so Scala is a dangerous language because it's got every bits and bobs and weird thing you could ever imagine, and you can really hang yourself with it. But Martin Odursky's book, on the other hand, is really good. I finally learned how combinator parsing works with that book.
Would you recommend skipping Haskell and going straight from Scala to Idris?
No, because the engineering environment for Idris is not nearly as mature. There's not thousands of libraries and all that kind of stuff. And the compiler is probably slower, and the community is not as big. You're not going to get Stack Overflow answers for everything and all that kind of stuff.
Cool. Thanks.
On the other hand, Haskell will have these strange distinctions, things that could look strange if you came at it from this angle, strange distinction between types and values and stuff like that.
Yeah, and this is like much more clear to understand. And I mean, in Haskell, when you write like type level function, they are completely different, right? You say type family, and then you don't use any arrows, and
right.
This is like totally strange for Haskell that you have 2 different ways of write functions. Oh.
Yeah.
I just want to show you one thing that I found one paper from Oleg Kiselyev about object capabilities.
Ooh.
It's about the lightweight object capabilities. So
can you give some intro? What's object capabilities are?
Well, then it's much more into the subject.
I do have a short version though. I've read that paper, or I know. Anyway, the short introduction to capabilities. Suppose that when you went to drive your car, instead of sticking a key in, you stuck your driver's license up to a little reader, and it said, "Oh yeah, that's Dan. You're allowed to drive the car." Right?
Okay.
And then and your daughter has her driver's license, and she's out driving, and she breaks her arm, and so she'd really like her friend to drive her to the hospital, but her friend sticks her driver's license up to the car, and it says, "You can't drive the car."
Okay.
So that's the way pretty much all computing is done today. Unix and all this kind of stuff is done with access control lists, where the car has a list of drivers.
Yeah.
Right. And you can make groups, and then you can add somebody to the group and all this kind of stuff. But it doesn't compose very well. And so if you do it the other way around, if you have keys, then I can just hand the key to you, and then you can drive the car. So that's a very short introduction to capabilities versus access controls.
Thanks.
So then you said you read this paper.
Yeah. Maybe
It says that you can somehow encode in the type. You say you also supply function that give you proof for this defining function. So for example,
yeah, they end up being static capabilities, right?
Yeah, exactly.
Yeah.
But it's interesting. This is like a lightweight capability, right? You say, in my list there is no like a nullable element, and you supply this function that calculates this. But you don't do this for every execution. You must somehow protect all of these constructors, and you can say really that this function that you are saying that defines this capability or constraint capability, that really is.
Oh. Yeah. So if you want a thing where at compile time you can tell that your system has the security properties you want, this is kind of cool. On the other hand, you do have to compile your whole program, and for me the interesting thing about capabilities is how you can combine programs at runtime. Foreign code and mobile code is remote code execution becomes a feature, not a bug.
Yeah.
And so the paper that I'm working on in particular, the one that I've been showing you guys, is about when you can prove something about part of the code, but then there's a bunch of other code that you don't know anything about it, and you can say that the system is still cool. And it's just like I don't know if you've read the stuff about pi calculus. You've got process one in parallel with who knows what, right?
But you want to say something about this other thing, so some kind of constraint or
right. You can say things like, okay, I just made up this new name, and so nobody else knows it. So the whole rest of the world doesn't know this new thing I just made up, right? But yeah, the reason I think those sort of open world things are more interesting is it's like, okay, I want to know that my bank is secure, even though it lives in this whole world, and I don't want to have proven something about the entire United States financial system, or the whole world's financial system before I can know that my bank is okay. I just want to know copies about my bank. So this paper is kind of cool, but after I had understood it, I was like, oh no, I don't want that.
they're saying, you only need some kind of generation on some type in compile time, and but this is not easy. You must generate something in compile time. So yeah, but they're saying that this way of defining like constraints, it's a little less syntax than independently typed language. So that is like interesting.
Huh. All right, my dogs are getting to the end of their patience, so I'm going to have to.
Yeah. Thanks, Dan.
Yeah,
Thanks
thanks,
for
Dan.
being a good audience.
Thank you very much. Thanks for your advices.
See you.
Bye all.
Have a good day.
Bye-bye.
Thank you.
You too.
Okay, able to stop it.